Hi everyone, it's Shamika, and today I'll be going over a couple updates on the LCPC Shapes Handbook. So first we'll get into a quick rundown of the presentation. The first chapter of the handbook describes what the LCPC transform actually is, including the individual steps. Then, through chapters 2 to 4, we'll move on to the shapes and examples. Near the end of the presentation, I'll go over some of the next steps to this project. So as I just mentioned, Chapter 1 of the handbook focuses on explaining the LCPC transform, which stands for the Linear Compressed Polar Coordinate Transform. So the first step in this process involves the translation of a simple shape into a set of polar coordinates. This can be achieved through two separate approaches. The first is the vertical parallel grid system, in which, as the name states, vertical lines are placed upon a figure with an equal distance separating them, and wherever the shape intersects with each line, a point is created and marked. Next, we have the radial grid system, where lines radiate from one central point, and these are overlaid upon a figure. And in a similar fashion to the system before, the points where the figure intersects with each line is marked with a particular point. Then, after collecting this data, we can move on to the actual compression part, where all points on one line are summed to lead to one value. When these sum values are plotted on a chart, the pattern will be a discrete sinusoid wave. This data is often difficult to visualize, so the last step in this process utilizes the fast Fourier transform to transform the sinusoid graph into a frequency plot, which portrays the magnitude at each frequency. The parameters of the fast Fourier transform is up to the user, such that there can be any number of frequency bins. The user just has to objectively apply the same parameters across comparison groups. That was just a brief description of the LCPC transform. Now we'll move on to the actual Shapes handbook. First, we'll go over a general summary of the handbook. Our main purpose in creating this is to create a way for the audience to develop a visual intuition of the LCPC transform. Chapter 1 follows what I just described in the slides before. We'll move on to Chapter 2, which allows our audience to visualize this method through simple and complex open shapes. Then, Chapter 3 turns to the differences noted with closed shapes. And Chapter 4 dives into the LCPC transform application to engineering and physical sciences. I'll begin by going over a quick intro on how to read and interpret the graphs. So, the top row will be the actual shape, and each shape has a mini blue line on the bottom right corner, which is the reference mark. On the following examples, we'll be using the vertical grid system, and thus we'll need to define where the origin or reference point is because the algorithm for the LCPC searches for the bottom edge of the figure. With this mark, we can effectively measure the distance between the shape and the origin line. When we add the reference mark, we are adding information to the shape, but when we add it consistently to every shape we can compare these shapes objectively. Then we'll move on to the middle row, which portrays the frequency spectrum derived by the fast Fourier transform, which is basically the result for the shape above it. Now we'll go to the bottom row, which is the same graph as the frequency spectrum, but with a truncated y-axis so that we can see the small bars more clearly and appreciate the difference of the magnitudes of each bar. By our default setting for the fast Fourier transform, we always have 19 frequency bins, but this is arbitrary. We'll begin by jumping into some general shapes laid together side by side, or section 2A. Please turn your focus to the third row, or panels G, H, and I, which depict a stark difference in the comparative magnitudes of each line. In these shapes, their ends are perfect horizontals, so the reference mark doesn't matter as much, but with shapes where one end is higher than the other, the reference mark matters a lot. So during this presentation, I'm going to be talking specifically about how the results of the LCPC transform are affected by a change in distance, a change in scale, and chirality or mirror imaging. 2B relies on portraying the effect of distance on the final result of the LCPC transform. This is the same shape, um, but each shape is a different height or a different distance from the blue reference line. Specifically, from left to right, it goes higher and higher. When we look at the sum magnitude graph or panel G, it makes sense that as we move farther from the reference line, its sum magnitude increases. Also, there's a clear difference between the magnitude bars in the truncated FFT graphs, as noted with the bars of differing colors varying through differing heights in panel H. This handbook also displays distance through other figures, including a simple line, an open triangle, an open circle, and an open bow tie. Now we move on to 2C, which depicts more complex shapes. Showcasing features like this is vital because it often mimics the complexity of shapes encountered in biological tissues. Another special case includes sine waves, which vary in amplitude. This is another fundamental shape that we think scientists would be interested in knowing how it is seen by the LCPC transform. This shape also exemplifies how the LCPC transform handles shapes that fold and thus have multiple intersections per grid line. As you can see in panel H, the more folds a shape has, the larger its sum magnitude. However, in panel I, you can clearly see the nuance between how the LCPC sees these three shapes in a nonlinear fashion. In this example, we show how the introduction of a complex shape within a simple line changes the LCPC output. In panel H, the reason why the middle image has the highest sum magnitude is because the squiggly part of the shape is farthest away from the reference line. Though the same squiggly part is also in the shapes shown in panel C, the squiggly shape in panel C is closer to the reference line. This difference is due to an effective distance as described back in section 2b. Then, 2D reports the effect of size scale. We can see this through an open bow tie on on the slide, where the size of the figure decreases through each theme. This directly This directly affects the respective magnitude bars of each shape, which can be seen through panel G. Lastly, 2E describes the effect of chirality or mirror imaging. We chose these three approaches because it shows something very important about the LCPC in that if we want to include a reference mark like we did here, there is no one right way to include it. We'll be looking at this curved figure as an example. In approach one, the shape has a distinct frequency spectrum when flipped horizontally into its mirror image. The reference mark is kept on the bottom right in both cases. However, in approach two, where the curve is flipped as before, the reference mark is kept on the bottom left. This approach is equally valid. Furthermore, the reference lines or marks can be placed towards the imaginary mirror line as in approach 3. In each of these cases, the LCPC measures the flipped shape differently, as noted by the orange and blue bars. This shows the sensitivity of the LCPC transform in measuring what seems like a simple change in shape, like flipping it into its mirror image. Flipping an image doesn't change its area or its volume, but the LCPC transform can measure a form of spatial information that area and volume cannot. Now that we've covered chapter 2, I'll talk about some of the next steps for this handbook. So far, we've been looking at open shapes, so ideally our plan would be to extract full closed shapes and distinguish the results of the LCPC between these full shapes and the open shapes. Moreover, it's important that we show our audience that the LCPC transform can be applied to various applications in physical sciences in addition to brain tissue. By putting all these elements together, we can create a cohesive handbook effectively demonstrating the vast advantages of the LCPC transform over traditional measures of shape such as area, surface area, or volume. One example of an application of the LCPC transform to physics is optimizing the shape of an airfoil, otherwise known as a cross section of an airplane wing. Here, we can quantify both the top and bottom edge of the airfoil as seen in panels A, um, B, and C, or we can quantify just the top edge of the airfoil as seen in D, E, and F, or just the bottom edge as seen in panels G, H, and I. Any shape that needs the optimization of fluid flow around it or fluid mechanics can be precisely and quantitatively modeled by using the LCPC transform. We'll be looking at more applications in the future. Well, this is all I have for you today, but please let me know if you have any feedback or questions. Thank you for listening.